Hello there, and welcome back to the Science Sleepy Minds. Tonight, you're floating. Not in a bathtub, not in a lazy river, but in the absolute emptiness between galaxies, where the silence is so total it almost hums. Somewhere far below your dangling feet, if directions even mean anything out here. A point of absolute darkness is pulling at the fabric of space itself, bending starlight into graceful arcs the way a bowling ball warps a trampoline. That point has no surface, no solid ground, no welcome mat. It is a black hole, and tonight you're going to learn exactly how it was born. Fair warning, if you were actually this close to one, you probably would not survive the experience. Your body would be stretched into a piece of cosmic spaghetti thinner than a guitar string, which admittedly is a terrible way to spend an evening. But here in your bed, under your blanket, you are perfectly safe, and I promise the only stretching happening tonight is that slow, delicious stretch your legs do right before you drift off. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, drop a comment telling me where you're listening from and what time it is on your clock. I always love reading those. Someone in Tokyo at 3 in the morning, someone in Buenos Aires just after midnight, someone in a small town in Norway where the sun barely set 2 hours ago. Wherever you are, you're welcome here. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You tilt your head back and let your gaze wander across the star field. There are billions of them out here, tiny pinpricks of ancient light, each one a furnace of unimaginable heat, and every single one of those stars will die. That is not a morbid thought, it is simply the universe's way of recycling. Stars are born, they burn, they age, and eventually they exit the stage in one dramatic fashion or another. Some go quietly, puffing off their outer layers like a dandelion losing its seeds in a breeze. Others go out in the most violent explosions the cosmos has ever produced, and a rare, magnificent few leave behind something so extreme, so fundamentally strange, that even the laws of physics start to stammer and look at their shoes when you ask what is happening inside. That something is a black hole. And the question you're here to answer tonight, the question that has kept astrophysicists arguing over chalkboards and cold coffee for more than a century, is deceptively simple. How is a black hole actually born? Not what is a black hole, because you have probably heard the elevator pitch before. Not what would happen if you fell into one, because again, spaghetti. The question is about origins, about the exact sequence of events that takes ordinary matter, the same stuff that makes up your coffee table and your kneecaps, and crushes it into a region of space from which nothing, not even light, can escape. The story begins long before the black hole itself exists. It begins with the birth of a star. And to understand that, you need to picture something almost comically opposite to a black hole. Instead of a tiny, impossibly dense point, you need to imagine one of the largest, most diffuse structures in the entire universe. A giant molecular cloud. These clouds drift through galaxies like cosmic fog banks, stretching across dozens or even hundreds of light years. They are made mostly of hydrogen gas with a little helium mixed in, plus traces of dust, tiny grains of carbon and silicates no bigger than the particles in cigarette smoke. If you could scoop a cubic centimetre out of one of these clouds, you would find maybe 1,000 molecules in it. For comparison, the air you're breathing right now contains roughly 25 quintillion molecules in that same volume. So these clouds are fantastically empty by earthly standards. You could almost call them nothing at all. Almost. Because gravity does not care how thin a cloud is. Gravity is the most patient force in the universe. It never sleeps, it never gets bored, and it never, ever lets go. And inside these vast cold clouds, temperatures hovering around 10 degrees above absolute zero, colder than anything you have ever touched, colder than the surface of Pluto on its worst day, gravity begins to pull the gas inward, very slowly. A molecule here drifts toward a molecule there. Clumps form. Clumps attract other clumps. The process is glacial. We're talking hundreds of thousands of years before anything visibly exciting happens. Historians of astronomy still argue whether it was William Herschel or his sister Carolyn who first catalogued certain cloudy patches in the sky that we now know to be these stellar nurseries, though the full understanding of what they were would not come until the 20th century. And here is a quirky little detail for you. Some of these molecular clouds contain alcohol. Ethyl alcohol, the same kind in your weekend cocktail, floating in enormous quantities through interstellar space. There is a cloud near the constellation Aquila that contains enough ethanol to fill 400 trillion pints of beer. The universe, it turns out, has been brewing long before humans ever figured out fermentation. You lie still, imagining that cold, boozy fog drifting in the dark, and somewhere inside it a pocket of gas is growing just a little denser than its surroundings. That pocket of gas you're watching, barely a whisper of extra density in the vast freezing cloud, is about to become something spectacular. But it is in no hurry. You settle deeper into your pillow and let time accelerate. Centuries blurring past like highway lane markers at midnight, and gradually you see the clump pulling itself together. More molecules tumble inward. The clump grows heavier, and as it grows heavier, its gravitational pull strengthens. And as its gravitational pull strengthens, it attracts even more material from the surrounding cloud. This is what physicists call a runaway process, and it is beautifully simple. The more you have, the more you get. It is the cosmic equivalent of a snowball rolling downhill, except this snowball is light years across and made of hydrogen gas cold enough to freeze your soul. As the gas falls inward, something important happens. It heats up. You might think that compressing a gas should make it colder. After all, you're squeezing it into a smaller space, packing molecules closer together. But the opposite is true. When you compress a gas, the molecules bounce off each other more frequently and more energetically, and that frantic bouncing is exactly what temperature is. Think of the last time you pumped air into a bicycle tyre and noticed the pump getting warm in your hands. Same principle, just scaled up by a factor of, several trillion. The collapsing gas cloud is essentially pumping itself, gravity acting as the hand on the piston, and the core of this shrinking clump begins to glow with a faint infrared warmth. Astronomers call this a protostar, and it is the embryo of what will eventually become a full-fledged star. It cannot do any nuclear fusion yet. It is far too cool and too loosely packed for that, but it is on its way, and gravity is not about to stop pushing. The protostar sits at the centre of a swirling disk of leftover gas and dust, spinning slowly like cream stirred into coffee. This disk is where planets will eventually form, but tonight you're not interested in planets. You're interested in the star itself, because the star is the main character in the black hole origin story, and right now it is still in its awkward adolescence. Material from the disk keeps raining down onto the protostar's surface, adding mass, adding heat, adding pressure. Deep inside, the temperature climbs past 10,000 degrees, then 100,000, then 1,000,000. The gas is no longer a gentle fog. It is a screaming plasma. Atoms stripped of their electrons, everything moving so fast that collisions become genuinely ferocious. And then, at roughly 10 million degrees in the core, something magical happens. 2 hydrogen nuclei, just single protons, the simplest atomic nuclei in existence, slam into each other with enough energy to overcome their mutual electrical repulsion. Protons are positively charged, and positive charges repel each other. So under normal circumstances, two protons would bounce apart like tiny billiard balls. But at 10 million degrees, they are moving so fast that they barrel right through that repulsive barrier and get close enough for the strong nuclear force to grab hold. The strong force operates only at incredibly short range, shorter than the width of a proton itself, but once it grips hard. The two protons fuse together, releasing a burst of energy in the form of gamma rays and a positron. This is nuclear fusion, the same process that powers every star you have ever seen in the night sky. And the moment it ignites in the core of that collapsing gas cloud, a star is officially born. You might wonder who first figured out that stars run on nuclear fusion. Scholars still debate the relative contributions of Arthur Eddington, who in the 1920s boldly proposed that stars are powered by subatomic processes, and Hans Bethe, who in 1939 worked out the precise chain of reactions while reportedly riding a train to a conference. The legend goes that Bethe solved the problem of how stars shine partly as a way to pass the time during the commute, which either makes him the greatest train passenger in history or the worst dinner party storyteller, depending on your perspective. And here is a strange little footnote. Cecilia Payne-Gaposchkin had already demonstrated in her 1925 doctoral thesis that stars are made primarily of hydrogen, but her conclusion was so radical that her own advisor told her to downplay it. She was right, of course, and the boys caught up eventually. Astronomers still argue whether her thesis should be considered the single most important doctoral dissertation in the history of astrophysics, though it is hard to find a serious contender. Now, the newborn star does not just sit there quietly fusing hydrogen. The moment fusion begins, the energy pouring out of the core creates an outward pressure, radiation pressure and thermal pressure that pushes against the inward crush of gravity. And here, right here, is where the story of a future black hole truly takes shape. Because the star's entire life, from this moment until its spectacular death, is defined by a single, breathtaking balancing act. Gravity wants to collapse the star, fusion wants to blow it apart. And for millions or billions of years, depending on the star's mass, these two forces will hold each other in a perfect trembling stalemate. You can feel it, almost if you close your eyes. A tension, like a held breath. The star is not at peace. It is at war with itself, every second of every day. Gravity pulling inward, fusion pushing outward, and the whole glowing sphere hovering in a state of dynamic equilibrium that could, under the right circumstances, shatter in an instant. But that shattering is a story for later. Right now, the star is young, it is bright, and it has fuel to burn. Literally. You watch it flare to life in the darkness, a new point of light joining the billions already scattered across the sky. It looks so steady from out here, so calm, like a candle flame in a still room. But inside, it is an inferno of colliding particles and cascading energy, a furnace that would vaporize anything solid within millions of kilometers, and somewhere in your drowsy mind, you know that this beautiful, blazing thing is already on a path toward darkness. Every photon it releases, every wave of heat it pours into space, brings it one tick closer to the moment when the fuel runs out and gravity finally wins. But that moment is far, far away, and for now the star burns, and you breathe, and the night is quiet. You're still watching that newborn star, this furious ball of plasma hovering in the void, and from out here it looks almost serene. A gentle dot of white light, the kind of thing you might wish upon without a second thought. But inside, the star is locked in a struggle so fundamental, so relentless, that if either side gained even a slight advantage for more than a few moments, the entire structure would either fly apart like a firecracker or crumple inward like a sandcastle under a boot. This struggle has a name, and it is one of those beautiful phrases that physicists came up with on a good day: hydrostatic equilibrium. It sounds like something a yoga instructor might whisper during a particularly ambitious pose, but it is actually the single most important concept in stellar physics, and without it, there would be no stars, no planets, no you, and certainly no black holes. Here is how it works. You already know that gravity is pulling every bit of the star's material toward its centre. Gravity does not play favourites. It tugs on every atom, every ion, every stray electron, dragging everything inward with a quiet, implacable patience. Left unchecked, gravity would compress the star into the smallest possible volume, squeezing and squeezing until the density became absurd. But gravity is not unchecked. Down in the core, nuclear fusion is converting hydrogen into helium and releasing enormous amounts of energy in the process. That energy heats the surrounding plasma to tens of millions of degrees, and hot plasma exerts pressure, outward pressure, pushing against gravity's inward pull. The result is a standoff. At every layer of the star, from the blazing core to the relatively cool surface, the inward force of gravity is precisely matched by the outward force of pressure. Not approximately matched, precisely matched. The star adjusts itself constantly, a live-in feedback loop, so that if gravity gains a tiny edge and the star contracts a fraction, the core heats up, fusion rates increase, pressure rises, and the star puffs back out. If pressure wins and the star expands a little, the core cools, fusion slows, pressure drops, and gravity pulls it back in. It is the most elegant thermostat in the universe, and it works flawlessly for millions or billions of years. You let that sink in for a moment. Lying there in the dark, every star you've ever seen, every point of light in the night sky, is a sphere in perfect gravitational balance, humming along in this state of dynamic tension. The sun, that cheerful yellow presence that warms your face on a Saturday morning, has been maintaining hydrostatic equilibrium for roughly 4.5 billion years without a single day off. It does not get weekends. It does not get holidays. It just burns and balances, and it will continue doing so for another 5 billion years or so before things get interesting. But the sun is a relatively small star, a cosmic lightweight, and its eventual death will be gentle by astronomical standards. A slow, puffing up into a red giant, a shedding of outer layers, and a quiet retirement as a white dwarf. No black hole, not enough mass. The sun simply does not have the gravitational muscle to crush itself into oblivion. The stars you need to worry about, the ones that end up birthing black holes, are the heavyweights. Stars with at least 20 or 25 times the mass of the sun, though scholars still debate the exact threshold because it depends on factors like how fast the star is spinning and what its chemical composition looks like. These massive stars are rare. For every one of them born in a galaxy, there might be hundreds or thousands of smaller sun-like stars popping into existence. But they are extraordinary. They burn hotter, shine brighter, and live far shorter lives. A star with 30 times the sun's mass might exhaust its hydrogen fuel in just a few million years compared to the sun's leisurely 10 billion year career. That is the cruel irony of being a massive star. You are born with a colossal fuel tank, but you burn through it so recklessly fast that you flame out while your smaller siblings are still in their early middle age. And here is a fun little detail that sounds made up but is absolutely real. The most massive stars ever observed are so luminous that they are actually tearing themselves apart. A star called R13601 in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, was once estimated at over 300 times the mass of the Sun and roughly 10 million times as luminous. At that level of brightness, the radiation pressure from the surface is so intense that it blows off the star's own outer layers in ferocious stellar winds, like a fire hose pointed at a pile of confetti. The star is essentially too powerful for its own good, shedding mass continuously even as gravity tries desperately to hold it together. Astronomers still argue about the exact upper limit for stellar mass, whether stars can exceed a few hundred solar masses, or whether radiation pressure always wins and prevents them from growing any larger. It is one of those delightful open questions that keeps astrophysicists employed and caffeinated. Now, the reason massive stars matter so much to the black hole story is precisely because of hydrostatic equilibrium. Remember, the balance depends on fusion in the core producing enough outward pressure to counteract gravity. As long as the star has fuel to fuse, the balance holds. But fuel does not last forever, and when it begins to run out, the balance starts to wobble. In a small star like the Sun, this wobble leads to a graceful, slow decline. In a massive star, the wobble leads to catastrophe, because a massive star does not simply run out of fuel and fade. It runs out of one fuel and switches to another, then another, then another, climbing a ladder of increasingly desperate nuclear reactions, each one buying a little less time than the last. It is like watching someone pay off one credit card by opening another, then another, a frantic juggling act that can only end one way. You feel your eyelids growing just a little heavier as you picture that massive star out there, blazing away, gorgeous and doomed. It does not know what is coming. Stars, as far as we can tell, do not have premonitions. They just burn and balance and trust that the fuel will hold. And for now, it does. The fuel holds, but it is changing. Deep in the core of that massive star you've been watching, the hydrogen is running thin. Not gone, not yet, but the supply is dwindling, and the star can feel it in the only way a star can feel anything, which is through the math of pressure and temperature and the relentless arithmetic of gravity. You sink a little deeper into your mattress and let your mind drift down into the heart of the star, past the blazing surface, past the radiative zone where photons bounce around like pinballs in slow motion, down into the core where the real action happens. And what you find there is a transformation so elegant it almost qualifies as art. For millions of years, the core has been fusing hydrogen into helium through a process called the proton-proton chain. 4 hydrogen nuclei go in, 1 helium nucleus comes out, and a little bit of mass disappears in the transaction, converted into pure energy according to that famous equation you've seen on t-shirts and coffee mugs. Einstein's equation, the one that says energy equals mass times the speed of light squared, and the speed of light squared is an enormous number, which is why even a tiny amount of mass converts into a staggering amount of energy. Every second, the sun alone converts roughly 4 million tons of matter into energy. 4 million tons just gone, transformed into photons that will take 100,000 years to random walk their way from the core to the surface before shooting off into space at light speed. Some of those photons, after their long journey, end up hitting your face on a Tuesday afternoon while you wait for a bus. You are, in a very real sense, being warmed by the annihilation of matter, but helium is accumulating in the core like ash in a fireplace. Helium nuclei are heavier than hydrogen nuclei, and they require much higher temperatures to fuse. So for a while, the helium just sits there, an inert lump growing slowly at the center of the star, doing nothing useful. In a smaller star, this helium buildup eventually causes a dramatic event called the helium flash, where the helium ignites all at once in a brief, violent burst. But in a massive star, the process is smoother. The core is already so hot and so dense that when the hydrogen fuel starts to dwindle, and the core contracts a little under gravity's squeeze, the temperature climbs naturally until it crosses the threshold for helium fusion, about 100 million degrees, and then the star begins burning helium into carbon. This is where fusion's ladder begins, and you should picture it as literally as possible. Imagine a ladder leaning against a wall, and each rung represents a heavier element. The star starts at the bottom rung, hydrogen, and with each step upward it fuses heavier and heavier elements, releasing energy at every stage. Hydrogen fuses into helium, helium fuses into carbon, carbon fuses into neon, neon fuses into oxygen, oxygen fuses into silicon, and silicon fuses into iron. Each rung is hotter than the last, each phase shorter than the one before, each transaction yielding a little less energy than the previous one. The star is climbing the ladder with increasing desperation, burning through each fuel source faster and faster, like a marathon runner who keeps picking up the pace even though the finish line is not getting any closer. The numbers are staggering. A massive star might spend millions of years burning hydrogen. It will burn helium for maybe a few 100,000 years. Carbon burning lasts perhaps 1,000 years. Neon burning, and this is where things start to feel rushed, takes roughly a year. Oxygen burning lasts a few months, and silicon burning, the final rung of the ladder, lasts about one single day. One day. After millions of years of steady hydrogen fusion, the star sprints through its last fuel source in 24 hours. If that does not strike you as ominous, you might want to check your pulse. Fred Hoyle, the brilliant and occasionally cantankerous British astronomer, was one of the first to work out the details of this nucleosynthesis ladder in the 1950s. Hoyle realised that the elements heavier than hydrogen and helium, the carbon in your DNA, the oxygen in your lungs, the calcium in your bones, were all forged inside the cores of massive stars through exactly this sequence of fusion reactions. He famously called it stellar nucleosynthesis, and the idea was so radical at the time that many of his colleagues were skeptical. Hoyle also predicted a specific energy state of the carbon nucleus, now called the Hoyle state, that had to exist for the fusion process to work. When experimentalists confirmed it, it was one of the great triumphs of theoretical astrophysics. Scholars still debate whether Hoyle deserved a Nobel Prize for this work. He never received one, despite being nominated multiple times, and some have speculated that his abrasive personality and his controversial rejection of the Big Bang theory, a term he himself coined somewhat mockingly, cost him the honour. The universe apparently does not reward sarcasm, and here is a peculiar little tidbit that might make you smile as you drift. The process by which helium fuses into carbon is called the triple alpha process, because it requires 3 helium nuclei, also known as alpha particles, to come together almost simultaneously. The odds of 3 particles colliding at exactly the right moment, with exactly the right energy, are astronomically small. It is like tossing 3 coins into the air and having them all land perfectly stacked on top of each other. The only reason it works at all is because of quantum mechanical resonances, specific energy levels that act like little shelves where the intermediate products can briefly rest before the 3rd particle arrives. Without those resonances, carbon would be vanishingly rare in the universe, and carbon-based life, which includes you, would never have happened. You owe your existence to a quantum coincidence inside a dying star, and that is perhaps the most astonishing thing you will hear tonight, though the night is still young. The star is climbing that ladder faster now, and you can almost feel the urgency even from your cozy vantage point, wrapped in blankets and half adrift in the dark. Each new fusion stage burns hotter, burns briefer, and produces a heavier element that settles toward the center of the star like sediment sinking to the bottom of a pond. And this settling is what gives the massive star its most beautiful and most terrifying internal structure, something astronomers call the onion layer model. You're about to peel back the layers of a dying giant, and what you find inside is going to look surprisingly like a cosmic vegetable. Picture the star in cross-section, sliced clean down the middle like an onion on a cutting board. The outermost layer, the part you would see if you were watching from a safe distance, is still mostly hydrogen. It is the original material the star was born from, and up here in the outer envelope not much has changed. The hydrogen is hot by earthly standards, thousands of degrees at the surface, but compared to what is happening deeper down, it might as well be a cool breeze. Beneath the hydrogen layer sits a shell of helium, the accumulated ash from millions of years of hydrogen fusion. This helium shell is itself undergoing fusion in a thin blazing band, converting helium into carbon and adding to the next layer down. Beneath the helium sits a shell of carbon. Beneath the carbon, a shell of neon. Beneath the neon, oxygen. Beneath the oxygen, silicon. And at the very centre, sitting like a dense, heavy seed at the heart of a fruit, is a core of iron. Each layer is thinner, hotter, and denser than the one above it. The temperature gradient is absurd. The surface of the star might be a few thousand degrees, while the core is measured in billions. The density increases just as dramatically. The outer layers are wispy and diffuse, barely denser than a terrestrial vacuum, while the core is packed so tightly that a teaspoon of it would weigh several tons. If you could somehow scoop out a thimbleful of the silicon-burning shell and drop it onto a kitchen scale, the scale would not just break, it would be crushed into the countertop. The whole structure is nested and concentric, each shell burning its own fuel, producing its own ash and feeding the layer below. It is, in a word, magnificent. It is also a ticking clock. The reason the onion structure matters so much is that it represents the star's final biography, written in elements. Each layer is a chapter, and the chapters are getting shorter. The outermost hydrogen layer took millions of years to produce. The innermost iron core will be built in a single day. The star is writing its autobiography at an accelerating pace, and the last chapter is going to be very, very brief. Eddington, that same Arthur Eddington who first proposed that stars are powered by subatomic energy, once wrote that a physicist who could not explain his work to a barmaid had not truly understood it himself. If Eddington could see the interior of a supergiant star rendered in modern computer simulations, with each fusion shell colour-coded and labelled, he would probably agree that it is one of the most intuitively graspable and simultaneously mind-boggling structures in all of astrophysics. Here is something that might surprise you. The onion layer model, as clean and elegant as it sounds, is actually a simplification. Real massive stars are messy. The boundaries between layers are not crisp lines, but turbulent, churning zones where convection currents carry hot material upward and cooler material downward, mixing elements across shell boundaries in complicated ways. Modern three-dimensional simulations of these stars reveal roiling, chaotic interiors where plumes of burning material rise and fall like bubbles in a lava lamp. Scholars still argue about the extent of this convective mixing and how it affects the star's evolution. Some models suggest that mixing can dredge up heavy elements from deep layers and deposit them near the surface, altering the star's appearance and spectrum. Others suggest that certain layers remain relatively isolated, burning quietly in their own little bubble. The truth is probably somewhere in between, and figuring out exactly where is one of the grand challenges of computational astrophysics. Supercomputers chew on these simulations for months at a time, and the results are still being refined. And now, a delightfully odd piece of trivia for your sleepy brain. The element neon, which you probably associate with garish signs outside diners and bowling alleys, is produced in one of the most ephemeral fusion stages in the entire onion structure. Neon burning lasts roughly 1 year in a massive star, a cosmological eye blink, and yet neon itself is the 5th most abundant element in the entire universe by mass. Most of that neon was cooked up in stars just like the one you're watching right now, in fusion shells that burned hot and fast and then were gone. Every neon sign you've ever seen is glowing with the recycled guts of ancient, dead stars. There is something almost absurdly poetic about that. The universe spends a year forging neon in a furnace of unimaginable heat, and humans use it to advertise cheap pizza. You're sinking now, you're breathing slow and even, and the star is sinking too. Layer by layer, the core grows heavier. The iron seed at the centre is expanding. Atom by atom, a silicon fusion feeds it from above. Iron does not glow any less than the other elements. It is incandescently hot billions of degrees, but it is fundamentally different from everything above it, because iron is the end of the line. Iron is where the fusion ladder runs out of rungs, and what happens when the star reaches for the next rung and finds nothing there is going to change everything. You feel the quiet weight of that approaching moment, the way you might feel the stillness before a thunderstorm. The star does not know it is about to die. It just keeps burning, layer by layer, shell by shell, beautiful and oblivious and running out of time, and you, lying here in the dark, know what is coming even if the star does not. That iron core is growing, and somewhere very close to the centre of this magnificent doomed structure, a clock is about to strike midnight. The iron core sits at the centre of the star like a clenched fist, and it is growing heavier by the hour. Silicon fusion in the shell just above it keeps raining fresh iron down onto its surface, adding mass, adding density, adding to the pressure that is building in a place where pressure is already beyond anything you could meaningfully imagine. You lie there in the dark and picture it. A sphere of iron roughly the size of Earth, but weighing more than the Sun, compressed so tightly that a cubic centimetre of it would outweigh an aircraft carrier. And this iron core, this dense and furious seed, is about to become the most important object in the entire star. Because iron is the element that breaks everything. To understand why, you need to know something about the economics of nuclear fusion. Every fusion reaction the star has performed up to this point, hydrogen into helium, helium into carbon, carbon into neon, and so on up the ladder, has been an energy-producing transaction. You put in 2 lighter nuclei, you get out one heavier nucleus, and the difference in mass between the inputs and the output is released as energy. This works because lighter nuclei are less tightly bound than heavier ones. So fusing them together moves you toward a more stable configuration, and nature rewards stability with a little burst of energy. It is like rolling a ball downhill. You move from a higher energy state to a lower one, and the difference is released as kinetic energy, or in this case, as radiation and heat. But iron sits at the very bottom of the hill. Iron 56, the most common isotope, has the highest binding energy per nucleon of any element in the universe. It is the most tightly bound, the most stable, the most energetically content nucleus there is. Fusing iron into something heavier does not release energy. It consumes energy. It is like trying to roll a ball uphill. You have to put energy in rather than getting energy out. And that is a catastrophic problem for a star that has been relying on fusion energy to hold itself up against gravity for millions of years. The moment the core becomes predominantly iron, the star has reached the end of its fuel supply. Not because it has run out of material to fuse, there is plenty of iron, but because fusing that material would cost more energy than it produces. The furnace has not gone out. The furnace has been presented with a bill it cannot pay. This realization, that iron represents a dead end for stellar fusion, was one of the great insights of 20th century astrophysics. Fred Hoyle and his collaborator William Fowler, along with the husband and wife team of Geoffrey and Margaret Burbidge, laid out the detailed nuclear physics in a landmark 1957 paper known simply as B²FH, after the author's initials. The paper is sometimes called the most important work in the history of nucleosynthesis, and it explained not only the iron dead end but the entire sequence of element-building reactions inside stars. Fowler would eventually share the 1983 Nobel Prize in Physics for this work, though scholars still argue about whether the Burbidges, and especially Hoyle, were unfairly excluded from the prize. The Nobel Committee has a long and complicated history with snubs, and the B²FH omissions remain one of the more contentious examples. Now here's where the doom really sets in. The iron core is not just sitting there passively, it is being squeezed by gravity, and without fusion to push back, the only thing supporting it is a quantum mechanical effect called electron degeneracy pressure. This is a strange and wonderful consequence of the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state in the same place at the same time. As the core compresses, the electrons are forced into higher and higher energy states because the lower ones are already occupied, and this resistance to further compression creates an outward pressure that temporarily holds the core up. It is not fusion, it is not heat, it is pure quantum stubbornness, electrons refusing to be squeezed into identical states, and for a brief, shining moment, it is enough. But the iron core keeps growing. Silicon fusion keeps dumping fresh iron onto it from above, and the core's mass climbs relentlessly toward a critical threshold. That threshold is called the Chandrasekhar limit, named after Subrahmanyan Chandrasekhar, the Indian-American astrophysicist who calculated it in 1930, while still a graduate student travelling by steamship from India to England. Chandrasekhar was just 19 years old when he worked out that a stellar core supported by electron degeneracy pressure cannot exceed roughly 1.4 times the mass of the Sun. Beyond that limit, electron degeneracy pressure fails. The electrons, no matter how stubbornly it resists, simply cannot generate enough pressure to counteract gravity. Chandrasekhar's result was initially ridiculed by Eddington himself, who found the implication that a sufficiently massive core would collapse without limit, philosophically repugnant. The disagreement between Chandrasekhar and Eddington became one of the most famous feuds in the history of physics, and it took decades for the scientific community to fully accept that Chandrasekhar was right. He received the Nobel Prize in 1983, more than 50 years after his original calculation, which gives you some idea of how slowly the universe of academic recognition moves. And here is a quirky little detail that might lodge in your drowsy brain. Chandrasekhar reportedly performed his groundbreaking calculation using the back of an envelope during that steamship voyage across the Indian Ocean. The journey took about 18 days, and somewhere between Madras and Southampton, a teenager with a pencil and a scrap of paper essentially predicted the existence of a mass limit that would underpin the entire theory of stellar death. You're lying in a comfortable bed with a phone in your hand and access to the collected knowledge of the human race, and a 19-year-old on a boat with an envelope changed astrophysics forever. Let that thought settle gently into your evening. The iron core is approaching that limit now. You can almost hear it creaking, the quantum scaffolding straining under the impossible weight. And when the core crosses the Chandrasekhar limit, everything that happens next will happen faster than you can blink. The core crosses the limit, and the collapse begins. Not slowly, not gracefully, not with any kind of warning that a human mind could register. The iron core, that Earth-sized sphere of the densest matter the star has ever produced, simply gives way. Electron degeneracy pressure, the quantum stubbornness that has been propping up the core for the last frantic hours of silicon burning, is overwhelmed. Gravity, patient and unrelenting and victorious at last, seizes the core and drags it inward at a speed that defies comfortable metaphor. You're lying still in the dark, breathing softly, and in the time it takes you to draw a single breath, the core of this star collapses from the size of the Earth to the size of a city, about 100 kilometers across, in less than a second. Let that settle over you like a heavy blanket. A sphere 8,000 miles wide, containing more mass than the Sun, compresses itself into a ball roughly the width of a medium-sized metropolitan area in under 1 second. The material at the outer edge of the core is falling inward at something like 70,000 kilometers per second, about a quarter of the speed of light. If you have ever dropped a glass off a kitchen counter and marvelled at how fast it hit the floor, multiply that feeling by a factor of several 100 billion, and you are in the right neighbourhood. This is not a gentle settling. This is a freefall implosion of almost incomprehensible violence, and it is happening in the heart of a star that, from the outside, still looks perfectly normal. The outer layers have not yet received the memo. Light travels fast, but the collapse is happening so deep inside the star that the surface will not know anything is wrong for several more seconds. The star is already dead at its core. It just does not know it yet. As the core plummets inward, the density skyrockets. Within milliseconds, the collapsing material reaches densities that dwarf anything in ordinary human experience. At these densities, the protons and electrons in the iron nuclei are squeezed together so forcefully that they merge, combining through a process called inverse beta decay to form neutrons and neutrinos. The protons swallow the electrons essentially and become neutrons. Electrically neutral particles that can be packed far more tightly than atoms because they lack the electromagnetic repulsion that keeps ordinary matter fluffy. The neutrinos, ghostly particles that barely interact with matter at all under normal circumstances, are produced in such staggering quantities during this collapse that they carry away an almost unbelievable amount of energy. In the span of about 10 seconds, the collapsing core releases more energy in the form of neutrinos than the Sun will produce in its entire 10 billion year lifetime. That is not a typo. 10 seconds versus 10 billion years. The neutrino burst from a core collapse is one of the most energetic events in the universe, and almost all of it is invisible because neutrinos pass through ordinary matter like wind through a chain-link fence. In 1987, astronomers got their first direct confirmation of this neutrino burst when a star exploded in the Large Magellanic Cloud, a small companion galaxy to the Milky Way. The event, designated Supernova 1987A, was the closest observed supernova since Kepler's supernova in 1604, and a handful of neutrino detectors around the world, instruments buried deep underground to shield them from cosmic ray noise, picked up a pulse of about 24 neutrinos arriving over a span of 13 seconds. 24 might sound pathetically small, but considering that neutrinos are so reluctant to interact with matter that a single neutrino could pass through a wall of lead a light year thick without stopping, detecting even 24 of them was a triumph. Scholars still debate whether the slight time difference between the neutrinos detected at different observatories reveals anything about neutrino mass, or was simply an artifact of the small sample size. It remains one of the most analysed datasets in the history of particle astrophysics, 24 tiny signals that confirmed a theory about the death of stars. Now back inside the collapsing core, the material has become almost entirely neutrons. It is, in effect, a giant atomic nucleus, 100 kilometers across and denser than anything you have ever contemplated. A teaspoon of this neutron-rich material would weigh roughly 6 billion tons on Earth, which is more than the combined weight of every human being who has ever lived, packed into a volume smaller than a sugar cube. At this point, a new form of pressure kicks in. neutron degeneracy pressure, the neutron equivalent of the electron degeneracy pressure that failed earlier. Neutrons, like electrons, are fermions, particles that obey the Pauli exclusion principle, and they resist being squeezed into identical quantum states. This resistance creates an outward push that, for cores below a certain mass, is strong enough to halt the collapse. And here is where the bounce happens. The infalling material from the outer core, still raining down at a quarter of the speed of light, slams into this suddenly rigid ball of neutrons and rebounds. It is like dropping a bowling ball onto a trampoline and watching the surface snap back. The bounce sends a shock wave racing outward through the still collapsing layers above, a wave of compressed superheated material moving at tens of thousands of kilometers per second. This shock wave is the embryo of the explosion that will follow, but it is not yet strong enough on its own. The shock wave stalls. It runs into the infalling material and loses energy, slowing down, struggling, on the verge of fizzling out entirely. If the shock wave dies, there is no explosion. The star simply swallows itself whole. Something has to revive the shock wave, and the answer, improbably, is those neutrinos. You feel your thoughts softening at the edges, your body heavy and warm, and somewhere inside a collapsing star, the faintest particles in the universe are about to save the show. The shock wave is stalling, and for a fraction of a second the entire future of the star hangs in the balance. If the shock dies, everything collapses inward and the story ends in silence. But those neutrinos, that incomprehensible flood of ghostly particles streaming outward from the newborn neutron core, are about to perform a miracle of statistics. Individually, neutrinos are the loners of the particle world. They pass through matter almost without noticing it. A single neutrino could fly through the entire Earth and never bump into a single atom. But the key word here is almost. At the densities present just above the neutron core, with material so tightly packed that even light would struggle to push through, even neutrinos have a small but meaningful chance of interacting. And when you have an almost inconceivable number of neutrinos, something on the order of 10 to the 58th power, which is a 1 followed by 58 zeros, even a tiny interaction probability adds up to an enormous energy transfer. You can think of it this way. Imagine standing in a rainstorm where every raindrop is so small and so light that any single drop has almost no chance of making you wet. But there are so many drops, trillions upon trillions upon trillions of them, falling so densely that you end up drenched anyway. The neutrinos deposit a fraction of their energy into the stalled shockwave, reheating it, reinvigorating it, giving it the push it needs to start moving outward again. This mechanism is called the neutrino-driven explosion, and it is the leading theoretical explanation for how core collapse supernovae actually work. It is also, somewhat embarrassingly, one of the least settled questions in all of astrophysics. Scholars still argue about whether neutrino heating alone is sufficient to revive the shockwave, or whether other effects, convection, rotation, magnetic fields, instabilities with names like SEISI, the standing accretion shock instability, play essential supporting roles. Three-dimensional computer simulations of core collapse have been running on the most powerful supercomputers in the world for decades, and they are only now beginning to consistently produce successful explosions. For years, the simulations kept failing. The shock wave would stall, the neutrinos would not deposit enough energy, and the star would collapse into a black hole without ever exploding. It was deeply frustrating for the theorists, who knew from observation that real stars do explode, and yet could not get their models to cooperate. The universe, it turned out, was hiding some important subtlety in the details, but the shockwave does revive. Whether it is the neutrinos alone or some combination of factors, the outward moving wave of energy gathers strength, ploughing through the infalling material, heating it to billions of degrees and accelerating it outward. And now the explosion truly begins. The shockwave tears through the onion layers you explored earlier, through the silicon shell, the oxygen shell, the neon, the carbon, the helium, the hydrogen. And as it rips through each layer, it compresses and heats the material so violently that new fusion reactions ignite. Elements that the star never had time or temperature to create during its lifetime are forged in the passage of the shockwave. Gold, platinum, uranium, all the elements heavier than iron that cannot be produced by ordinary stellar fusion, are cooked up in the few seconds it takes the shockwave to traverse the star's interior. This process is called explosive nucleosynthesis, and it is one of the primary ways the universe manufactures its heaviest elements. The gold in your jewellery, the platinum in catalytic converters, the uranium in nuclear reactors, all of it was born in the death throes of massive stars, forged in a shockwave moving at a significant fraction of the speed of light. The outer layers of the star struck by the shockwave are blown outward into space at tens of thousands of kilometers per second. This is the supernova, the most powerful explosion in the universe short of the Big Bang itself, and it is as visually spectacular as it is physically extreme. For a few weeks, a single exploding star can outshine an entire galaxy of 100 billion stars. It pours energy into space across the entire electromagnetic spectrum, visible light, X-rays, gamma rays, radio waves, and scatters heavy elements into the interstellar medium, seeding the gas clouds from which future generations of stars and planets will form. Remember those giant molecular clouds from the beginning of our journey. Those cold, diffuse fog banks of hydrogen and dust where new stars are born. The dust in those clouds, the carbon and silicon and iron that will eventually become rocky planets and the bones of living creatures, was placed there by supernovae just like this one. You are made of star stuff, as Carl Sagan loved to remind people, and the delivery mechanism for that star stuff was a shockwave from a dying giant. Here is a historical nugget to tuck under your pillow. In the year 1054, Chinese astronomers recorded the sudden appearance of a brilliant new star in the constellation we now call Taurus. It was so bright that it was visible in broad daylight for 23 days and remained visible to the naked eye at night for nearly 2 years. They called it a guest star. What they were seeing was a supernova, and the remnant of that explosion is still visible today as the Crab Nebula, a gorgeous filamentary cloud of glowing gas expanding outward from the site of the blast. And nestled at the centre of the Crab Nebula, spinning 30 times per second and emitting beams of radiation like a cosmic lighthouse, is a neutron star, the compressed core left behind by the explosion. In this case, the core was not quite massive enough to become a black hole, but for stars with heavier cores, the story does not end with a neutron star. The story goes darker. You breathe in slowly, and somewhere in the wreckage of an exploded star, a core is still collapsing, and the darkness is waiting. The wreckage is expanding outward in every direction, a glorious shell of superheated gas and freshly minted heavy elements, painting the void with colour and light. But you are not looking outward. Your gaze is drawn inward, toward the centre of the explosion, where something has been left behind. The shockwave carried the outer layers of the star into space, but the core, that impossibly dense ball of neutrons, remains. It is sitting in the middle of the expanding debris like a stone at the centre of a detonated building, and what happens to it next depends on one single, crucial number: its mass. If the core's mass is below a certain threshold, neutron degeneracy pressure holds. The neutrons push back against gravity with enough force to stabilise the core, and what you get is a neutron star. These are extraordinary objects in their own right. A neutron star is typically about 20 kilometers across, small enough to fit comfortably inside a mid-sized city. But it contains 1 to 2 times the mass of the Sun. The density is almost cartoonishly extreme. That teaspoon weighing 6 billion tons you heard about a couple of sections ago, that was neutron star material. The surface gravity is about 200 billion times the gravity on Earth, which means that if you dropped a marshmallow onto a neutron star from a height of 1 meter, it would hit the surface with the energy of a small nuclear weapon. Neutron stars can also spin incredibly fast, some rotating hundreds of times per second. Their magnetic fields trillions of times stronger than Earth's. They are, by any reasonable standard, among the most exotic objects in the known universe. But they are not black holes. For a core to become a black hole, it needs to exceed a higher mass threshold, and this is where a limit known as the Tolman-Oppenheimer-Volkoff limit enters the story. Named after Richard Tolman and the duo of J. Robert Oppenheimer and George Volkoff, who worked out the physics in 1939, this limit represents the maximum mass that a neutron star can sustain before neutron degeneracy pressure, combined with the repulsive component of the strong nuclear force between neutrons, is no longer sufficient to resist gravitational collapse. The exact value of this limit is one of the most actively debated numbers in astrophysics. Current estimates place it somewhere between 2 and 3 solar masses, but pinning it down precisely requires understanding the behavior of matter at densities so extreme that no laboratory on Earth can replicate them. Scholars still argue about the equation of state for neutron-rich matter at supranuclear densities, essentially the relationship between pressure and density inside a neutron star. And different models yield different values for the maximum mass. Every time a new neutron star mass measurement is published, theorists scramble to see whether it constrains the equation of state further. Oppenheimer himself, the same man who would later lead the Manhattan Project and become famous for quoting the Bhagavad Gita after the first nuclear test, co-authored the seminal 1939 paper on this topic with his student Volkoff. The paper is titled On Massive Neutron Cores, and it calmly concludes that a sufficiently massive core will contract indefinitely, with no known physical mechanism capable of halting the collapse. Oppenheimer and Volkoff did not use the term black hole, that would not be coined until decades later, but they understood the implication. Beyond a certain mass, gravity wins absolutely, and the core collapses past every barrier physics can erect. And here is a peculiar detail about the timing of that paper. It was published on September 1st, 1939, the exact same day that Nazi Germany invaded Poland and World War II began. One of the most important papers in the history of gravitational physics arrived on the same morning as one of the most devastating events in human history, and it went largely unnoticed by a world suddenly preoccupied with survival. Science, as it turns out, does not always get to choose its moment. So what happens when the core exceeds the Tolman-Oppenheimer-Volkoff limit? Neutron degeneracy pressure fails. The strong nuclear force, which provides additional repulsion between neutrons at very short range, is overwhelmed, and the core, already denser than an atomic nucleus, collapses further. There is no next rung on the pressure ladder. Electron degeneracy failed at the Chandrasekhar limit. Neutron degeneracy fails at the Tolman-Oppenheimer-Volkoff limit. And as far as known physics is concerned, there is no third type of degeneracy pressure waiting to catch the fall. Some theorists have speculated about exotic forms of matter, quark stars for instance, where neutrons themselves are crushed into their constituent quarks, or strange stars composed of strange quark matter. But even these hypothetical states of matter would have their own maximum mass. And beyond that, the collapse continues. You feel the pull of it now, lying there in the softness of your bed, your thoughts heavy and slow. The core is falling inward with nothing to stop it. The density is climbing beyond anything that exists in the observable universe outside of a black hole. Space-time itself is beginning to warp in ways that would make your head spin if your head were not already comfortably nestled into your pillow. And somewhere in that shrinking, darkening core, a boundary is about to form. A boundary from which nothing, not matter, not light, not information of any kind can ever return. The event horizon is about to be born, and with it, a black hole will enter the universe for the first time. The core is still falling. There is no floor, no wall, no quantum mechanical stubbornness left to arrest the collapse. Gravity has won every battle it was ever going to fight, and now it is simply collecting the spoils. The material that was once iron, once neutrons, once the dense heart of a magnificent star, is compressing beyond any state of matter that physics has a confident name for. And as this happens, as the density climbs and the radius shrinks, something extraordinary is happening to the geometry of space and time around it. You need to think about space-time for a moment, and the easiest way to do that while you're lying here half asleep is to imagine a rubber sheet stretched flat. Place a marble on the sheet and it creates a small dimple. Place a bowling ball and the dimple becomes a deep well. Now imagine placing something so heavy and so compact on the sheet that the well becomes infinitely deep, a bottomless funnel from which the rubber surface curves so steeply that nothing rolling along it could ever climb back out. That is a loose, imperfect, but genuinely useful picture of what is happening around the collapsing core. The mass is warping space-time so severely that paths through space, even paths travelled at the speed of light, curve back inward. Light itself, the fastest thing in the universe, the cosmic speed limit that nothing with mass can ever reach, is being bent and trapped by the curvature of space-time. The boundary where this trapping becomes absolute is the event horizon. It is not a physical surface. There is no wall there, no membrane, no glowing fence with a sign that reads, "Abandon all hope." If you were falling toward it, you would not feel anything special at the moment you crossed it. There is no bump, no flash, no alarm bell. The event horizon is a mathematical boundary, defined by the geometry of space-time, and it marks the point beyond which the escape velocity exceeds the speed of light. Inside the event horizon, every possible path through space-time leads inward, toward the centre of the collapse. It does not matter how fast you move or in which direction you point yourself. The geometry of space itself has been so thoroughly warped that inward is the only direction that exists. Trying to move away from the centre inside the event horizon would be like trying to move backward in time outside it. Not just difficult, not just impractical, but literally meaningless within the framework of physics as we understand it. The radius of the event horizon is called the Schwarzschild radius, named after Karl Schwarzschild, a German physicist who derived the first exact solution to Einstein's field equations of general relativity in 1916. Schwarzschild's achievement is remarkable on several levels, not least because he did it while serving on the Eastern Front during World War I, performing complex mathematical calculations in the trenches between artillery bombardments. He sent his solution to Einstein in a letter, and Einstein, who had only recently published his general theory of relativity and had not yet found an exact solution himself, was reportedly astonished. Schwarzschild died just a few months later from a painful autoimmune disease contracted during his military service, never knowing the full significance of what he had discovered. His solution described the space-time geometry around a perfectly spherical, non-rotating mass, and embedded within it was the prediction of the event horizon, a boundary where the math went haywire and the standard description of space and time broke down. Scholars still debate whether Schwarzschild himself understood the physical implications of this boundary or regarded it as a mathematical curiosity with no real-world counterpart. And here is a fact that might make you blink in the dark. The Schwarzschild radius of any object is proportional to its mass, and the formula is breathtakingly simple. Take the mass, multiply by 2, multiply by Newton's gravitational constant, and divide by the speed of light squared. That is it. For the Sun, the Schwarzschild radius works out to about 3 kilometers, meaning that if you could somehow compress the entire Sun into a sphere 3 kilometers across, roughly the length of a large shopping mall, it would become a black hole. For the Earth, the Schwarzschild radius is about 9 millimeters. A marble-sized Earth would be a black hole. You could hold the event horizon of a compressed Earth between your thumb and forefinger, though you absolutely should not try, for reasons that would become apparent almost immediately and catastrophically. The event horizon of the black hole forming from our collapsing stellar core has a radius of perhaps 10 to 30 kilometers, depending on the mass of the remnant. It is forming right now in the space of milliseconds, as the core's density crosses the critical threshold. From the outside, if you were watching from a safe distance, you would not see the event horizon pop into existence with any dramatic fanfare. What you would see is the light from the collapsing surface growing dimmer and redder as photons struggle harder and harder to escape the deepening gravitational well. This is gravitational redshift. Photons lose energy climbing out of a gravity well, and losing energy means their wavelength stretches, shifting them from visible light toward infrared, then microwave, then radio waves, until they fade beyond detection entirely. The last photons to escape from just outside the forming event horizon are redshifted into oblivion, stretched to infinite wavelength, carrying zero energy. The surface does not vanish with a pop. It fades, like a whisper trailing off into silence. And just like that, where there was once a star, there is now a region of space-time that has sealed itself off from the rest of the universe. The black hole is born, and the night around you feels just a little bit deeper. You have watched the event horizon form, that invisible boundary where light itself surrenders, and now your drowsy mind wants to know what lies beyond it. What is inside the black hole? What happens to all that matter, all that mass, all those neutrons and quarks and whatever else the collapsing core has been crushed into? The honest answer, the answer that physicists will give you after a long pause and a heavy sigh, is that nobody truly knows. But the mathematics of general relativity, Einstein's beautiful and maddening theory of gravity, makes a prediction that is as elegant as it is disturbing. The math says that the collapsing matter does not stop at any finite density. It does not reach some ultimate state of compression and stabilize. It keeps going, shrinking and compressing without limit, until all the mass is concentrated in a single point of zero volume and infinite density. That point is called the singularity, infinite density, zero volume. These are not comfortable concepts. They are not the kind of phrases that lull you gently to sleep, and they are not the kind of predictions that make physicists feel confident about their equations. Because in physics, when your math gives you an infinity, it usually means something has gone wrong. Not with the universe seems to be doing just fine, but with your description of it. Infinities in physics are almost always a signal that your theory has been pushed beyond its domain of validity, that you're trying to use a tool in a situation it was never designed to handle. And that is exactly what most physicists believe is happening at the singularity. General relativity, for all its extraordinary success in describing gravity on scales from falling apples to orbiting galaxies, is a classical theory. It does not account for quantum mechanics, the other great pillar of modern physics, which governs the behaviour of matter at the smallest scales. And at the singularity, you have an enormous amount of mass compressed into an infinitesimally small space, which means both gravity and quantum mechanics should be important simultaneously. You need a theory of quantum gravity to describe what is actually happening there, and as of right now, humanity does not have one. This is one of the most profound open problems in all of physics, and it has been driving theoretical physicists slightly mad for the better part of a century. Scholars still argue fiercely about what replaces the singularity when quantum effects are properly accounted for. Some approaches, like loop quantum gravity, suggest that quantum effects create a repulsive force at extremely high densities, preventing the collapse from reaching zero volume and instead producing a tiny but finite core of mind-boggling density. Others, working within string theory, propose that the singularity is resolved by the fundamental one-dimensional objects called strings, which have a minimum size and cannot be compressed to a point. Still others have suggested that the singularity might be a gateway to another region of spacetime entirely, a baby universe budding off from our own, or a white hole spewing matter into some other cosmos. These ideas range from the mathematically rigorous to the cheerfully speculative, and none of them has been confirmed by observation, because the singularity is hidden behind the event horizon and sends no information to the outside universe. That hiddenness, by the way, is not just an inconvenience for curious physicists, it might be a fundamental feature of the universe. In 1969, the British mathematician and physicist Roger Penrose proposed something called the cosmic censorship conjecture, which states, roughly, that singularities are always hidden behind event horizons and never visible to the outside universe. A naked singularity, one without an event horizon, would be a catastrophe for physics because it would allow the breakdown of predictability to leak out and infect the rest of space-time. Penrose's conjecture has never been rigorously proven, and scholars still argue about whether exceptions might exist under extreme or contrived conditions. But every known physical process that creates a singularity also creates an event horizon around it. The universe, it seems, has a sense of modesty. It wraps its strangest secrets in darkness and dares you to find a way to peek inside. Here is a delightful little detail about Penrose that you might enjoy as your eyelids grow heavier. Before he became famous for his work on black holes and singularities, Penrose was deeply interested in geometry and tiling patterns. He invented what are now called Penrose tiles, a set of shapes that can tile an infinite plane without ever repeating. These non-periodic tilings turned out to have deep connections to quasi-crystals, a bizarre form of solid matter that was discovered in the 1980s and was so unexpected that the discoverer Dan Shechtman was initially mocked by his colleagues before eventually winning the Nobel Prize. Penrose himself won the Nobel Prize in Physics in 2020 for his work on black holes, sharing it with Andrea Ghez and Reinhard Genzel, which means the man who tiled floors with impossible patterns also helped prove that spacetime can fold itself into impossible shapes. Some people contain multitudes, so the singularity sits at the center of the black hole, hidden behind the event horizon, a place where the known laws of physics confess their inadequacy. You do not need to understand it fully. Nobody does. But you can hold the shape of the mystery in your mind as you lie here, a point of infinite question, wrapped in a sphere of absolute darkness, sitting in the ruins of what was once a star. The black hole is complete now. It has an event horizon, it has a singularity, and it has begun its long, quiet existence in the universe. But the story of how black holes are born does not end with a single collapsing star. There are other paths to darkness, other ways the universe builds these extraordinary objects, and the next one involves scales so vast they make our stellar black hole look like a grain of sand on an endless beach. The black hole born from that collapsing star is drifting now through the galaxy, a silent, invisible presence with a mass perhaps 5 or 10 or 30 times that of the Sun. It is what astronomers call a stellar mass black hole, and it is far from alone. The Milky Way, that glowing river of light you can see on a clear dark night if you're lucky enough to be far from city lights, is estimated to contain somewhere between 100 million and 1 billion of these objects. 1 billion black holes scattered throughout a single galaxy, each one the remnant of a massive star that burned too bright and died too violently. You're surrounded by them right now, in a cosmic sense. The nearest one could be just a few thousand light years away, drifting through the stellar neighbourhood like a shadow with mass. And yet, for all their abundance, stellar mass black holes are extraordinarily difficult to find. This is the central paradox of black hole astronomy. The defining feature of a black hole is that it emits no light. It is, by definition, invisible. You cannot point a telescope at a patch of sky and see a black hole the way you see a star or a nebula. So how do astronomers know they exist? How do you find something that is defined by its absence? The answer, for most of the history of black hole observation, has been to look not at the black hole itself, but at its effect on things around it. A black hole that happens to be near another star, in a binary system for instance, where 2 objects orbit each other, can reveal itself through the havoc it wreaks on its companion. If the black hole is close enough, its gravitational pull can strip material from the companion star, peeling gas off the outer layers like unwinding a ball of yarn. This stolen gas does not fall directly into the black hole. Instead, it spirals inward, forming a swirling disk of superheated material called an accretion disk. As the gas spirals closer to the event horizon, friction and compression heat it to millions of degrees, and it begins to emit X-rays, high-energy photons that can be detected by space-based X-ray telescopes. The black hole itself is invisible, but its dinner plate is glowing. The first strong candidate for a stellar mass black hole was Cygnus X1, an X-ray source in the constellation Cygnus discovered in 1964 during a rocket-borne X-ray survey. Cygnus X1 is a binary system where a massive blue supergiant star is being slowly devoured by an unseen companion. By measuring the orbital motion of the visible star, astronomers calculated that the invisible companion had a mass of roughly 15 solar masses, far too heavy to be a neutron star, which meant it had to be a black hole. The identification was not immediately accepted. Stephen Hawking famously made a bet with his colleague Kip Thorne in 1974 that Cygnus X1 was not actually a black hole. Hawking later conceded the bet in 1990 as the evidence became overwhelming, reportedly paying off with a 1-year subscription to a magazine of Thorne's choice. Scholars still enjoy debating whether Hawking made the bet sincerely or as a form of insurance. He once said that if black holes turned out not to exist, at least he would have the consolation of winning a bet. Since Cygnus X1, dozens of stellar mass black holes have been identified in X-ray binary systems throughout the Milky Way and nearby galaxies. Each one was found the same way, by detecting the X-rays from superheated gas spiraling into an unseen object too massive to be anything else. But these are only the black holes that happen to have a companion star close enough to feed from. The vast majority of stellar mass black holes in the galaxy are isolated, drifting alone through interstellar space, accreting nothing, emitting nothing, completely and utterly silent. Finding these solitary black holes is one of the great challenges of modern astronomy. One method that has shown promise is gravitational microlensing. Remember that a black hole warps spacetime around it, and that warped spacetime bends the path of light passing nearby. If a black hole drifts between Earth and a distant background star, the black hole's gravity can act as a lens, temporarily brightening and distorting the background star's light. The effect is subtle and brief, lasting days to weeks, and it requires monitoring millions of stars simultaneously to catch the rare alignments. But it works. In 2022, astronomers announced what they believe to be the first definitive detection of an isolated stellar mass black hole using microlensing, a dark object about 7 solar masses drifting through the Milky Way roughly 5,000 light-years from Earth. The discovery was the culmination of years of painstaking observation and analysis, and scholars still argue about whether the mass estimate is precise enough to rule out the possibility that the object is an unusually massive neutron star rather than a true black hole. And here is a thought to carry with you into the deeper part of the night. For every stellar mass black hole we have found, there are millions we have not. They are out there right now, scattered through the galaxy like invisible potholes in the fabric of spacetime, each one a tomb of a star that lived fast and died young. Some are spinning rapidly, dragging spacetime around them like a whirlpool. Some are perfectly still, as close to motionless as anything in the universe can be. Some may have planets orbiting them, worlds that circle a point of darkness instead of a point of light, locked in stable orbits that will last for billions of years. The universe is full of these quiet remnants, and they are only the smallest members of the black hole family. Because somewhere far away, at the centre of nearly every large galaxy in the observable universe, something much, much bigger is lurking. And the story of how those monsters were born is stranger than anything you have heard so far. You shift slightly under your blanket, adjusting to a more comfortable position, and as you do, your mind makes a leap across an almost unimaginable gulf of scale. The stellar mass black holes you've been learning about, those remnants of dead stars with masses of 5 or 30 or maybe 50 suns, are impressive, but they are pebbles compared to the monsters that live at the hearts of galaxies. You are about to meet the supermassive black holes, and the word supermassive does not even begin to do them justice. At the centre of our own Milky Way, roughly 26,000 light-years from the patch of Earth where you're lying right now, there is a black hole called Sagittarius A star. Its mass is approximately 4 million times that of the Sun. 4 million suns compressed into a region of space-time with an event horizon about the size of Mercury's orbit. That is large enough to swallow our entire inner solar system, Mercury and Venus, and Earth, and Mars, without even noticing. And Sagittarius A star is considered modest by supermassive standards. The black hole at the centre of the galaxy Messier 87, the one that was famously photographed by the Event Horizon Telescope in 2019, has a mass of roughly 6.5 billion solar masses. Its event horizon is larger than our entire solar system, including the far-flung orbits of Neptune and Pluto and the scattered icy bodies beyond. If you placed it where our Sun is, its shadow would extend past the heliopause, the boundary where the solar wind gives way to interstellar space. These objects are not just big, they're a different category of big, a scale so far beyond ordinary experience that your brain essentially shrugs and gives up trying to picture it, which is probably healthy. The great mystery of supermassive black holes is not that they exist. We have overwhelming evidence that they do, but how they got so enormous. Stellar mass black holes are born from dying stars, and that process is well understood. But you cannot build a 4 million solar mass black hole by simply smashing stellar mass black holes together. The math does not work, or rather, it works but takes far too long. The universe is only about 13.8 billion years old, and astronomers have discovered supermassive black holes that were already billions of solar masses within the first billion years after the Big Bang. That is an absurdly short amount of time to grow a black hole from stellar mass to supermassive through ordinary accretion and merging. It is like finding a fully grown oak tree in a garden that was only planted last Tuesday. Something unusual must have happened during the early universe to produce these monsters so quickly, and figuring out what that something was is one of the most active and contentious areas of research in modern astrophysics. There are several competing theories, and they can be broadly grouped into two categories: those that start with small seeds and grow them rapidly, and those that start with large seeds and grow them more gradually. The small seed models begin with the kinds of stellar mass black holes you already know about. In the early universe, the first generation of stars, called population 3 stars, were likely far more massive than most stars today, perhaps hundreds of times the mass of the Sun, because the primordial gas from which they formed contained no heavy elements, which meant it could not cool as efficiently and tended to collapse into larger clumps. These titanic first stars would have burned through their fuel in just a few million years, and then collapsed into black holes with masses of perhaps 100 to 1,000 solar masses. These seed black holes could then have grown by accreting surrounding gas and merging with each other. But the growth rate is limited by something called the Eddington limit, which is the maximum rate at which a black hole can swallow material before the radiation from the infalling gas blows the remaining material away. It is like trying to eat soup while someone blows on the spoon. The Eddington limit means there is a natural cap on how fast a black hole can grow through accretion, and even with generous assumptions about sustained feeding, small seeds struggle to reach supermassive sizes within the available time. Scholars still argue about whether exotic conditions in the early universe, denser gas environments, lower radiation backgrounds, rapid merger events, could have allowed small seeds to grow faster than the Eddington limit would normally permit. Some models invoke episodes of super-Eddington accretion, where the inflow of gas is so chaotic and three-dimensional that the radiation escapes sideways while material continues to pour in from above and below. Others suggest that frequent mergers between seed black holes and the crowded environments of early galaxies could have accelerated the growth. The debate is lively and unresolved, with new observational data from telescopes like the James Webb Space Telescope adding fresh fuel to the arguments almost monthly. And here is a quirky detail about those population 3 stars, the very first stars in the universe. Despite being central to our theories about how supermassive black holes began, not a single population 3 star has ever been directly observed. They existed so early and burned out so quickly that we have never caught one in the act of shining. Everything we know about them comes from theoretical models and indirect evidence, like the chemical fingerprints they left in later generations of stars. They are the ghosts of the cosmic dawn, and the black holes they may have birthed are the seeds of the largest structures in the universe. It is a beautiful chain of inference, linking things we cannot see to things we can barely comprehend, and you can let that chain unspool gently in your mind as the night deepens around you. The small seed models are elegant and intuitive, starting with familiar physics and scaling up. But there is another possibility, one that skips the star phase entirely and jumps straight to the main event. This is the direct collapse model, and it is one of the more radical ideas in contemporary astrophysics. You lie there and let your mind drift back to the very early universe, less than 1 billion years after the Big Bang, when the cosmos was a simpler but far more turbulent place. Galaxies were still assembling themselves from vast halos of dark matter and primordial gas, and the conditions in some of these young proto-galaxies may have been just right for something extraordinary to happen. Picture a massive cloud of primordial gas, mostly hydrogen and helium, sitting at the centre of a dark matter halo. In the normal course of events, this gas would cool down, fragment into smaller clumps and form stars, just like the molecular clouds you encountered at the beginning of our story. But cooling requires specific conditions. Gas cools by radiating energy away, and the most efficient way for primordial gas to radiate is through the formation of molecular hydrogen. which can emit infrared photons and carry heat away from the cloud. If molecular hydrogen forms in abundance, the gas cools efficiently, fragments, and makes stars. But what if something prevents the molecular hydrogen from forming? What if there is an intense bath of ultraviolet radiation from nearby young stars, or from the first quasars, a radiation field strong enough to dissociate molecular hydrogen as fast as it forms? In that case, the gas cannot cool efficiently. It remains hot and smooth, unable to fragment into star-forming clumps, and instead it collapses as a single, coherent mass under the pull of gravity. This is the direct collapse scenario. Without fragmentation, without star formation, the entire cloud, containing perhaps 10,000 to 100,000 solar masses of gas, falls inward as one enormous blob. The collapse proceeds rapidly, and instead of forming a star that later dies and leaves behind a black hole, the gas either forms an incredibly massive short-lived object called a quasi-star, which is essentially a star with a black hole growing in its belly, or it collapses directly into a black hole without ever shining as a normal star at all. The resulting seed black hole could have a mass of 10,000 to 100,000 solar masses right from the beginning, far larger than any stellar remnant and a much more comfortable starting point from which to grow into a supermassive giant through subsequent accretion and merging. The direct collapse model has a certain audacious elegance to it, but it is also extremely finicky about its requirements. The conditions have to be just right. You need a massive enough gas cloud, you need the right dark matter halo, and critically, you need that intense ultraviolet radiation field to suppress molecular hydrogen formation and prevent the gas from cooling and fragmenting. This means the cloud needs to be relatively close to a source of ultraviolet light, another young galaxy perhaps, or an early population of hot stars, but not so close that other disruptive effects, like tidal forces or galactic winds, tear the cloud apart before it can collapse. The Goldilocks zone for direct collapse is narrow, and scholars still argue about how common these conditions were in the early universe. Some calculations suggest that direct collapse events were exceedingly rare, producing only a handful of seed black holes across the entire observable universe. Others argue that the conditions were more widespread than previously thought, especially in certain regions of the cosmic web where multiple young galaxies clustered together and bathed each other in ultraviolet radiation. In 2016, a team of astronomers reported the discovery of a peculiar object in the early universe, designated CR7, that initially appeared to be a strong candidate for a direct collapse black hole. The object was extraordinarily luminous, showed spectral signatures consistent with primordial gas containing almost no heavy elements, and seemed too bright to be explained by ordinary stars alone. The announcement generated enormous excitement and several breathless headlines about the first direct evidence of a direct collapse black hole. But subsequent observations muddled the picture, and later analysis suggested that CR7 might instead be a cluster of unusually hot young stars rather than a collapsing gas cloud. The debate over CR7 is still not entirely settled, and it illustrates just how difficult it is to identify direct collapse events observationally. You are looking for something that, by its nature, exists only briefly and in the most distant reaches of the observable universe, where the light has been travelling for more than 12 billion years and arrives faint and smeared by cosmic expansion. Here is a strange little wrinkle that might tickle your sleepy brain. The quasi-star, that hypothetical intermediate stage where a massive star harbours a growing black hole in its core, would have been one of the most bizarre objects ever to exist. Imagine a star so large that its core has already collapsed into a black hole, but the outer layers are still supported by the energy released as gas falls into the central black hole. The star is being powered by its own internal destruction. It is eating itself from the inside out, and the radiation from the accretion process is what keeps the outer envelope inflated. Models suggest that quasi-stars could have been enormous, perhaps 1 billion kilometers in radius, dwarfing any normal star, and they would have glowed with a strange reddish luminosity before finally losing the battle and collapsing entirely into the black hole at their centre. No quasi-star has ever been observed, and they may never be, but the concept lives on in theoretical models as a bridge between gas clouds and supermassive seeds. You settle deeper, feeling the weight of cosmic time pressing softly against your eyelids, and somewhere in the young universe, enormous things are falling into darkness. The seeds have been planted whether through stellar death or direct collapse, or some combination of mechanisms that the universe has not yet fully confessed to us. But black holes do not just sit still and grow in isolation. They move through space-time, they encounter each other, and sometimes in the most energetic events since the Big Bang itself, they collide. You're about to witness a black hole merger, and the universe has given you front row seats in the form of gravitational waves, ripples in the fabric of space-time that carry information about the most violent collisions in the cosmos directly to detectors on Earth. The story begins with 2 black holes in orbit around each other. Maybe they were born as a pair, the remnants of 2 massive stars that lived and died in a binary system, each one collapsing into a black hole while remaining gravitationally bound to the other. Or maybe they were once strangers, brought together by the gravitational dynamics of a dense stellar cluster, where close encounters and 3-body interactions can pair up black holes that originally had nothing to do with each other. However they met, they are now locked in a gravitational waltz, orbiting their common centre of mass in slowly tightening spirals. The spiralling is caused by gravitational wave emission. Every orbiting system radiates gravitational waves, ripples in space-time predicted by Einstein's general relativity in 1916, and as those waves carry energy away from the system, the orbit shrinks. For ordinary systems like the Earth orbiting the Sun, the energy loss is so minuscule that it would take longer than the age of the universe to have any noticeable effect. But for 2 black holes orbiting close to each other, each one packing several solar masses into a region smaller than a city, the gravitational wave emission is intense. The orbit decays measurably, and the 2 black holes spiral closer and closer together, orbiting faster and faster as they go. In the final moments before collision, they are whipping around each other hundreds of times per second, each orbit tighter and more frantic than the last, the gravitational waves growing louder and higher in frequency in what physicists call a chirp, a rising wail of space-time vibration that crescendos at the moment of merger. And then they touch. The event horizons of the 2 black holes make contact and merge into a single, larger, wildly distorted event horizon. The merged black hole is not spherical at first. It is lumpy and asymmetric, quivering like a struck bell, and it radiates away the excess energy of its distorted shape in a final burst of gravitational waves called the ring-down. Within milliseconds, the new black hole settles into a smooth, stable configuration described by just 2 numbers, its mass and its spin. All the complexity of the merger, all the chaos of the collision, is erased. The final black hole is clean, elegant, and featureless. Physicists sometimes describe this with the phrase, "black holes have no hair," a theorem that states that a black hole is completely characterized by its mass, charge, and angular momentum, and nothing else. The phrase was popularized by John Wheeler, the same American physicist who coined the term black hole itself in 1967, reportedly during a lecture at NASA's Goddard Institute. Scholars still argue about whether Wheeler actually invented the term or simply amplified it after hearing it from an audience member, but it stuck, and the physics community has been grateful for the vivid branding ever since. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected gravitational waves for the first time in human history. The signal, designated GW150914, came from the merger of two black holes roughly 36 and 29 solar masses in size, located about 1.3 billion light-years from Earth. The collision produced a final black hole of about 62 solar masses, and the missing 3 solar masses, the difference between the combined input and the final output, had been radiated away as pure gravitational wave energy in a fraction of a second. 3 solar masses converted entirely into ripples in space-time. For that brief moment, the merger was radiating more energy than all the stars in the observable universe combined. Let that wash over you as you lie there. More energy than every star in every galaxy, pouring out not as light but as vibrations in the geometry of space and time. The detection was a triumph decades in the making. LIGO had been conceived in the 1980s, funded through years of skepticism and budget battles, and upgraded multiple times before achieving the sensitivity needed to detect the almost incomprehensibly faint signals of gravitational waves. The mirrors in LIGO's detectors had to be sensitive to displacement smaller than 1/10,000th, the width of a proton. That is like measuring the distance from Earth to the nearest star and being able to detect a change of less than the width of a human hair. The Nobel Prize in Physics was awarded in 2017 to Rainer Weiss, Kip Thorne, and Barry Barish for the detection, and here is a wistful footnote. Ronald Drever, the third co-founder of LIGO, had died earlier that year and was ineligible for the posthumous honour. The Nobel Prize is not awarded after death, a rule that has arguably produced more quiet injustice than any other in the history of science. Since that first detection, LIGO and its European counterpart Virgo have observed dozens of black hole mergers, each one adding to our understanding of how black holes are born, how they grow, and how they find each other across the vast emptiness of space. You breathe out slowly, and somewhere in the universe, 2 black holes are spiraling toward each other right now, their merger still years or centuries or millennia away. A slow dance that will end in a shout of warped space-time. The mergers are spectacular, but they are not the only alternative origin story the universe has to offer. There is another possibility, one that reaches back not to the death of stars or the collision of remnants, but to the very first moments of existence itself. You're about to travel further back in time than you have gone all night, past the formation of the first stars, past the condensation of the first atoms, past the era when the universe was a blinding fog of plasma, all the way back to the first fraction of a second after the Big Bang. And there, in the unimaginable heat and density of the newborn cosmos, a very different kind of black hole may have been born. These are called primordial black holes, and the idea is both simple and tantalizing. In the first moments after the Big Bang, the universe was not perfectly smooth. It was almost smooth, astonishingly uniform on large scales, but it contained tiny fluctuations in density, regions where the matter and energy were packed just a little more tightly than the average, and regions where they were just a little more sparse. You can see the imprint of these fluctuations today in the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space. Those subtle variations in the microwave background, mapped with exquisite precision by satellites like COBE, WMAP and Planck, are the fossils of quantum fluctuations that occurred during or just after inflation, the brief period of exponential expansion that stretched the universe from subatomic to cosmic size in an unthinkably short time. Now, most of those density fluctuations were small. They seeded the large-scale structure of the universe, galaxies, galaxy clusters, the vast cosmic web, but they were not extreme enough to collapse under their own gravity in the early universe. However, the possibility exists that some fluctuations were much larger than average. If a region of the early universe was sufficiently overdense, it could have collapsed directly into a black hole before the universe had time to expand and dilute it. No star required. No fusion, no onion layers, no iron core, no supernova. Just a patch of the primordial plasma that was dense enough and compact enough to trap itself behind an event horizon through sheer gravitational self-compression. The idea was first proposed in the early 1970s by Stephen Hawking, and, independently, by the Soviet physicist Yakov Zeldovich. Hawking's contribution came in a 1971 paper that laid out the basic conditions under which primordial black holes could form and speculated about their possible masses. And this is where the concept gets wonderfully strange, because primordial black holes are not confined to any particular mass range the way stellar mass black holes are. A stellar mass black hole has to be at least a few solar masses, because that is the minimum required to overwhelm neutron degeneracy pressure, but a primordial black hole could in principle have any mass at all, from less than a gram to millions of solar masses, depending on the size and amplitude of the density fluctuation that produced it. The very smallest primordial black holes, those with masses much less than the mass of an asteroid, would have already evaporated through a process you will hear about soon. But primordial black holes in a certain mass range, roughly between the mass of an asteroid and the mass of a star, could still be drifting through the universe today, completely intact, relics of the first second of cosmic history. And here is where the story takes its most provocative turn. For decades, astronomers have known that roughly 85% of the matter in the universe is dark matter, a mysterious substance that exerts gravitational influence but does not emit, absorb, or reflect light. Despite enormous experimental effort, no one has directly detected a dark matter particle. No experiment has produced a confirmed signal. Every underground detector, every particle collider, every space-based observatory has come up empty. This has led some physicists to wonder whether dark matter might not be made of exotic new particles at all. What if it is made of primordial black holes? The idea is controversial but surprisingly difficult to kill. Primordial black holes would be dark by definition. They emit no light. They would interact with other matter only through gravity, exactly like dark matter. And if they formed in sufficient abundance in the early universe, they could account for some or all of the missing mass. Scholars still argue vigorously about whether the observational constraints allow primordial black holes to make up a significant fraction of dark matter. Various observations, microlensing surveys, the cosmic microwave background, the distribution of wide binary stars, the dynamics of dwarf galaxies, each rule out primordial black holes in certain mass ranges, but there remain windows, particularly around the mass of small asteroids and around tens of solar masses, where the constraints are less tight and the possibility has not been firmly excluded. Here is a quirky tidbit for your drifting mind. If primordial black holes with masses around 30 solar masses do exist in significant numbers, they might explain an unexpected feature of LIGO's detections. Remember those first gravitational wave signals from merging black holes? Several of the detected black holes had masses in the range of 20 to 40 solar masses, which some astrophysicists found surprisingly heavy for black holes formed from ordinary stellar evolution. Could some of LIGO's black holes actually be primordial, born not from dying stars but from the quantum jitters of the infant cosmos? The debate continues, and every new gravitational wave detection adds another data point to the argument. You lie there in the dark, a creature made of atoms, contemplating the possibility that the invisible scaffolding holding galaxies together might be made of tiny pockets of spacetime that sealed themselves off from the rest of the universe before atoms even existed. You have watched black holes born from dying stars, from collapsing gas clouds, from the mergers of existing remnants, and possibly from the quantum tremors of the Big Bang itself. Each origin story ends the same way: matter or energy compressed beyond the point of no return, an event horizon sealing off a region of space-time, and a new black hole entering the universe. But now you need to hear something that might seem contradictory, something that a young physicist in a wheelchair worked out in 1974 and promptly stunned the entire scientific community. Black holes are not forever. They can die. And the man who figured out how is the same man who made the bet about Cygnus X1 and lost a magazine subscription. Stephen Hawking was already famous in physics circles for his work on singularity theorems and the mathematical properties of black holes, when he turned his attention to the question of what happens when you apply quantum mechanics to the event horizon. Classical general relativity says nothing can escape a black hole, but classical general relativity does not know about quantum field theory, the framework that describes how particles and fields behave at the subatomic scale. And when Hawking brought quantum field theory to bear on the curved spacetime near an event horizon, he discovered something astonishing. Black holes radiate, they emit particles, they have a temperature, they glow faintly and almost imperceptibly, with a thermal radiation that now bears his name: Hawking radiation. The mechanism is subtle and deeply counterintuitive, so settle deeper into your pillow and let it wash over you without demanding perfect clarity. In quantum field theory, empty space is not truly empty. The vacuum is a seething, bubbling cauldron of virtual particle pairs, a particle and its antiparticle popping into existence for the briefest of moments before annihilating each other and vanishing back into nothing. This happens everywhere, all the time, and under normal circumstances it has no lasting effect. But near the event horizon of a black hole, something peculiar can happen. A virtual particle pair pops into existence just outside the horizon, and before the two particles can reunite and annihilate, one of them falls across the event horizon into the black hole, while the other escapes into space. The escaping particle becomes real. It carries real energy and can be detected, at least in principle, by an observer far away. The particle that fell in carries negative energy. From the perspective of the external universe, which means the black hole's total energy, and therefore its mass, decreases by a tiny amount. The black hole has lost a little bit of itself. It has radiated. This process is fantastically slow for stellar mass black holes. The temperature of Hawking radiation is inversely proportional to the black hole's mass, which means that bigger black holes are colder. A black hole with the mass of our Sun would have a Hawking temperature of about 60 billionths of a degree above absolute zero, far, far colder than the cosmic microwave background, which currently sits at about 2.7 degrees above absolute zero. This means that stellar mass and supermassive black holes are actually absorbing more energy from the background radiation of the universe than they are emitting through Hawking radiation. They're getting bigger, not smaller. In the current era of the universe, Hawking radiation is utterly negligible for any black hole we have observed or are likely to observe, but the universe is patient, and time is long. As the cosmos continues to expand and cool, the temperature of the cosmic microwave background will eventually drop below the Hawking temperature of even the most massive black holes. When that happens, trillions upon trillions of years from now, black holes will begin to evaporate in earnest. They will shrink, losing mass particle by particle, and as they shrink, they will get hotter, and as they get hotter, they will radiate faster. And as they radiate faster, they will shrink more quickly in a runaway process that accelerates toward the end. The final moments of a black hole's evaporation are predicted to be dramatic, a burst of high-energy particles and radiation as the last remnants of mass are converted into energy. Some physicists have described it as a small explosion, others as a flash of gamma rays, and scholars still argue about the exact details of what happens in the final instant when the black hole's mass approaches zero, and the semi-classical approximation that Hawking used breaks down. Here is a historical detail that adds a layer of poignancy to the story. When Hawking first announced his result, many of his colleagues did not believe him. The idea that black holes could radiate seemed to contradict everything that general relativity had established about event horizons being absolute boundaries. Hawking himself was reportedly unsure at first, spending weeks rechecking his calculations before he was confident enough to publish. The paper, which appeared in the journal Nature in 1974, is considered one of the most important contributions to theoretical physics in the 20th century. It bridged two of the great pillars of modern physics, general relativity and quantum mechanics, in a concrete, calculable way, and it revealed that black holes are not the permanent, immutable objects everyone had assumed them to be. They are thermodynamic systems with temperature and entropy, and they obey laws analogous to the laws of thermodynamics. And here is one of those quirky footnotes that seems almost too perfect. The entropy of a black hole, a quantity called the Bekenstein-Hawking entropy, is proportional not to the volume of the black hole but to the area of its event horizon. This is deeply strange. For every other physical system we know of, entropy scales with volume. But for black holes, all the information about their internal state is somehow encoded on the two-dimensional surface of the event horizon, like words written on the skin of a balloon. This peculiar fact would later inspire one of the most mind-bending ideas in all of physics, an idea you're about to encounter as your eyelids grow just a little heavier. The idea is called the information paradox, and it has been gnawing at the foundations of physics for half a century, like a mouse in the walls of a cathedral. You do not need to solve it tonight. Nobody has, not fully, not yet. But you should know what the argument is about because it touches on the deepest questions about what black holes are, what the universe is, and whether the laws of physics as we understand them are fundamentally consistent. So let your thoughts go soft and wide, and let the paradox settle into your mind the way a stone settles into sand. The problem begins with a principle that most physicists regard as sacred, the conservation of information. In quantum mechanics, information is never truly destroyed. If you know the complete quantum state of a system at one moment, you can, in principle, calculate its state at any other moment, past or future. The equations of quantum mechanics are reversible. If you burned a book, for instance, the information in that book is not gone. It has been scrambled and dispersed into the ash, the smoke, the heat, the light, the subtle correlations between trillions of particles, but it is all still there, encoded in the quantum state of the universe. A sufficiently powerful being with access to every particle involved could reconstruct the original book from the ashes. Information is conserved. This is not just a nice idea. It is a foundational axiom of quantum mechanics, woven into the mathematical structure of the theory at the deepest level. Now consider what happens when you throw something into a black hole. A book, a star, a cloud of gas, your car keys, whatever falls past the event horizon is gone from the external universe. It adds mass and angular momentum and charge to the black hole, but all the detailed information about what it was, its specific quantum state, its history, its structure, seems to vanish behind the horizon. This is already uncomfortable, but it gets worse. Hawking radiation, the process by which black holes slowly evaporate, is thermal. Thermal radiation is random. It carries no information about what fell into the black hole, any more than the heat radiating from a warm brick carries information about what was used to heat the brick. So if the black hole eventually evaporates completely, as Hawking's calculations predict it will, the information that fell in is apparently lost forever. It did not come out in the Hawking radiation. It is not stored in any remnant, because there is no remnant. The black hole is gone, and the information has seemingly been deleted from the universe. This is the paradox. Quantum mechanics says information cannot be destroyed. Black hole evaporation seems to destroy it. Both theories, quantum mechanics and general relativity, are extraordinarily well tested and successful in their respective domains, and yet they appear to contradict each other at the event horizon. Something has to give, and figuring out what has consumed some of the brightest minds in theoretical physics for decades, Hawking himself initially argued that the information was genuinely lost, that black holes really do destroy information, and that quantum mechanics needed to be modified to accommodate this. This position was bold, almost heretical, and it put him at odds with most of the quantum gravity community, particularly the string theorists. Leonard Susskind of Stanford and Gerard 't Hooft of Utrecht were among the most vocal opponents, arguing that information must be preserved and that the resolution would come from a deeper understanding of quantum gravity. The disagreement between Hawking and Susskind became one of the great intellectual rivalries of late 20th century physics, and Susskind later wrote a book about it called The Black Hole War, that reads almost like a thriller, if your idea of a thriller involves arguments about unitarity and the holographic principle. That holographic principle, by the way, emerged directly from the information paradox. Remember the Bekenstein-Hawking entropy, the strange result that a black hole's entropy is proportional to the area of its event horizon rather than its volume. 't Hooft and Susskind took this clue and ran with it, proposing that all the information contained within any volume of space can be encoded on the boundary of that volume, like a three-dimensional hologram projected from a two-dimensional surface. This idea, which sounds like science fiction but is supported by rigorous mathematical arguments within string theory, suggests that the information falling into a black hole is not lost inside it, but is somehow smeared across the event horizon, encoded in subtle quantum correlations in the Hawking radiation that only become apparent when you collect all of it and analyse it with impossible precision. Hawking eventually conceded the bet he'd made with John Preskill of Caltech, agreeing in 2004 that information is probably preserved after all. He presented a new calculation suggesting that quantum gravitational effects at the horizon could allow information to leak out in the Hawking radiation, though the details remained murky. Scholars still argue about whether Hawking's concession was fully justified by his calculation or was more of a graceful surrender to the weight of evidence and opinion from the string theory community. And here's a deliciously human detail about the bet. The agreed-upon prize was an encyclopedia because it represented information that could be retrieved. Hawking bought Preskill a baseball encyclopedia, and Preskill reportedly accepted it with good humour and mild confusion about the choice. The information paradox remains unsolved in any final, universally accepted sense. New proposals appear regularly, from firewalls that would incinerate anything crossing the event horizon, to the idea that the interior of the black hole is connected to the Hawking radiation by quantum wormholes called Einstein-Rosen bridges. Each proposal generates fresh arguments, fresh papers, and fresh conferences where physicists debate late into the evening over coffee and disagreement. You do not need to pick a side. You just need to know that the birth of a black hole sets in motion a puzzle so deep that it may ultimately require a complete rethinking of how space, time, and information fit together. The puzzles are deep, but the pictures are finally arriving. For most of the history of black hole science, these objects were theoretical constructs, predicted by equations, inferred from indirect evidence, but never directly seen. You knew they were there because of the X-rays screaming from accretion disks, because of the orbits of stars whipping around invisible partners, because of the gravitational waves chirping through space-time from mergers billions of light-years away. But you had never actually looked at one. That changed on April 10th, 2019, when a collaboration of over 200 scientists released the first direct image of a black hole's shadow, and the world collectively held its breath. The image showed the supermassive black hole at the centre of Messier 87, a giant elliptical galaxy in the Virgo cluster, roughly 55 million light-years from Earth. It was not a photograph in the traditional sense. You could not have taken it with a camera, no matter how large or expensive. The image was assembled from radio wave data collected by 8 radio telescopes scattered across the globe, from Hawaii to Spain to the South Pole, all synchronized to observe the same target at the same time using a technique called very long baseline interferometry. By combining the signals from telescopes separated by thousands of kilometers, the collaboration effectively created a virtual telescope the size of the Earth. This instrument, the Event Horizon Telescope, achieved an angular resolution so fine that it could, in principle, read a newspaper on the surface of the Moon. Not that anyone puts newspapers on the Moon, but the point stands. The resolving power was almost absurdly precise. What the image showed was a bright, slightly asymmetric ring of light surrounding a dark central region. The ring is the accretion disk, superheated gas swirling around the black hole at nearly the speed of light, glowing intensely in radio wavelengths. The dark centre is the black hole's shadow, the region where light has been captured by the event horizon and cannot reach the telescope. The asymmetry of the ring, brighter on one side than the other, is caused by relativistic beaming. The gas on the side of the disk moving toward Earth appears brighter because of Doppler effects, while the gas moving away appears dimmer. Every feature of the image was consistent with the predictions of general relativity. Einstein's equations, written over a century ago by a man who never imagined that anyone would build a planet-sized telescope, had predicted exactly what the shadow of a supermassive black hole should look like, and reality obliged. The achievement was staggering not only scientifically but logistically. The data collected by the 8 telescopes was so voluminous that it could not be transmitted over the internet. Instead, it was recorded on hard drives and physically shipped to central processing facilities. The hard drives from the South Pole telescope could not be shipped until the Antarctic winter ended and flights resumed, which meant the collaboration had to wait months for the final piece of the puzzle to arrive by cargo plane. There is something wonderfully human about that. An image of a supermassive black hole 55 million light-years away, delayed because a hard drive was stuck at the bottom of the world waiting for better weather. In May 2022, the Event Horizon Telescope released a second black hole image, this time of Sagittarius A star, the 4 million solar mass black hole at the centre of our own Milky Way. This image was in some ways even more challenging to produce than the Messier 87 image. Because Sagittarius A star is much less massive, the gas orbiting it moves faster and changes on shorter timescales, meaning the source was essentially flickering and shifting during the observation. The team had to develop new algorithms to account for this variability, combining thousands of possible images to produce a final composite that represented the average structure of the emission. The result was another glowing ring with a dark centre, confirming that our galaxy's central black hole looks just like theory predicted. Scholars still argue about the finer details of both images, the exact spin of the black holes, the precise geometry of the magnetic fields threading the accretion disks, the role of turbulence in shaping the emission. But the broad picture is clear and triumphant. And here is a detail that deserves a quiet smile as you settle further into the night. Katie Booman, a computer scientist then at MIT, developed one of the key imaging algorithms used by the Event Horizon Telescope team. She was 29 years old when the Messier 87 image was released, and a photograph of her reaction, hands over her mouth in disbelief as the image appeared on her laptop screen, went viral around the world. It became one of those rare moments where the human experience of scientific discovery was as powerful as the discovery itself. The picture of a young scientist seeing a black hole for the first time was, in its own way, as moving as the picture of the black hole. The next generation of instruments is already being planned. The next generation Event Horizon Telescope aims to add more dishes to the array, sharpen the resolution further, and eventually produce movies of gas swirling around black holes in real time. Space-based radio telescopes, orbiting above the atmosphere's interference, could extend the baselines beyond the diameter of the Earth and reveal even finer details. And gravitational wave detectors in space, like the planned LISA mission, will be sensitive to the low-frequency waves produced by supermassive black hole mergers, opening a window onto the births and collisions of the very largest black holes in the universe. You're living right now in the era when humanity went from inferring black holes to seeing them, and the view is only going to get sharper. You've come a long way tonight. From the cold, diffuse fog of a molecular cloud to the blazing heart of a massive star. From the frantic climb up fusion's ladder to the sickening freefall of core collapse. From the birth of an event horizon to the grand questions of information and entropy that still keep physicists awake long past their own bedtimes. You have watched black holes born from dying stars, imagined them sprouting from the direct collapse of primordial gas in the young universe, felt the space-time shudder of two black holes merging into one, and considered the possibility that some were seeded in the first fraction of a second after the Big Bang, relics of quantum fluctuations in a cosmos smaller than an atom. You have learned that black holes are not eternal, that they slowly radiate and may one day evaporate entirely, and that the information they swallow poses a puzzle so deep it may reshape our understanding of reality itself. And you have seen the first photographs, those luminous rings surrounding pockets of absolute darkness that confirmed what equations predicted a century ago. So why does any of this matter to you, lying here in your bed, your breathing slow, your thoughts soft and heavy? Why should the birth of a black hole, something that happens in the violent death throes of a star millions of light years away, mean anything to a person whose biggest concern tomorrow might be a grocery list, or a dentist appointment, or remembering to water the plants? Because you are made of the same stuff. Remember those supernovae, those titanic explosions that scatter heavy elements into the interstellar medium. The iron in your blood was forged in the core of a massive star, in one of those onion layers you peeled apart earlier tonight. The calcium in your bones was cooked up in a silicon burning shell. The oxygen you are breathing right now was fused in the belly of a star that died before our solar system even existed. Every atom in your body heavier than hydrogen and helium passed through the interior of a star and was liberated by an explosion. The same kind of explosion that leaves behind neutron stars and black holes. You are, in the most literal and unsentimental sense, a byproduct of the same process that creates black holes. You and the darkness were born in the same furnace, and the connection goes deeper than chemistry. The supermassive black holes at the centres of galaxies are not passive residents. They shape the evolution of their host galaxies in profound ways. When a supermassive black hole is actively feeding, swallowing gas and dust from its surroundings, it can produce jets of energy that extend thousands of light years into intergalactic space, heating the surrounding gas and regulating the rate at which new stars form. Without this feedback, galaxies might produce stars at a runaway pace, burning through their gas supply too quickly, or they might grow too large, too fast, disrupting the delicate balance of cosmic structure. Scholars still argue about the precise mechanisms of this feedback and how important it is to galaxy evolution. But the broad consensus is that supermassive black holes and their host galaxies co-evolve, each shaping the other in a gravitational and energetic dialogue that spans billions of years. The Milky Way is the shape it is, in part, because of Sagittarius A star. And you are here, on a small rocky planet in a quiet arm of that galaxy, because the galaxy evolved the way it did. The black hole at the centre of your galaxy is, in an indirect but very real sense, one of the reasons you exist. There is also the question of knowledge itself. Black holes sit at the intersection of general relativity and quantum mechanics, the two greatest theories in the history of physics, and they are the one place in the universe where both theories must be true simultaneously, and yet appear to contradict each other. Solving the puzzles posed by black holes, the information paradox, the nature of the singularity, the quantum structure of the event horizon, may ultimately lead to a unified theory of quantum gravity, a single framework that encompasses all the forces and all the phenomena in the universe. That theory, if it is ever achieved, would represent the deepest understanding of nature that the human mind has ever produced. And the road to that understanding passes directly through the heart of a black hole. Here is one last historical echo to carry with you into sleep. In 1783, a British clergyman and natural philosopher named John Michell wrote a paper speculating about what would happen if a star were so massive and so dense that light itself could not escape its gravitational pull. He called these hypothetical objects dark stars, and his reasoning, while based on Newtonian physics rather than general relativity, was remarkably prescient. Michel's dark stars were largely forgotten for nearly 2 centuries, overshadowed by the more rigorous predictions of Einstein and Schwarzschild and Oppenheimer. But the seed of the idea that gravity could swallow light was planted in the 18th century by a country parson with a curious mind and a quill pen. Scholars still debate whether Michel should be considered the true father of black hole theory, or merely an interesting footnote. But there is something lovely about the fact that the story of black holes begins with a clergyman staring at the sky and wondering what might be hiding in the dark. And now the night is folding softly around you, and the stars outside your window, if you have a window, are burning quietly in their own private balancing acts. Gravity against fusion, collapse against pressure, each one a story waiting to be told or a story already ending. You do not need to hold all of this in your mind at once. Let the details blur and soften, the way distant stars blur when your eyes lose focus. Let the iron core and the event horizon and the Hawking radiation dissolve into a gentle, luminous haze, like city lights reflected on low clouds. The universe is vast and strange and full of darkness, but the darkness is not empty. It is structured. It is dynamic. It has a birth story, just like everything else. And tonight, you heard it. Your breathing is slow now, deep and even, and the black hole at the centre of the galaxy is doing what it always does, sitting quietly, warping space-time in its gentle, implacable way, asking nothing of you, demanding nothing, just existing. The stars are burning, the clouds are drifting. Somewhere right now a massive star is running out of fuel and does not know it yet. Somewhere else 2 black holes are spiralling closer together, their merger still centuries away, the gravitational waves already beginning to build like a song too low for any instrument to hear. And you are here, warm and safe, made of star stuff and borrowed atoms, drifting towards sleep on a planet that orbits a quiet, middle-aged star that has billions of years of fuel left in its tank. There is no hurry. There is no urgency. There is only the slow, soft pull of rest, as gentle and as certain as gravity, drawing you down into the warm darkness where dreams are waiting. Let it carry you. Let the numbers fade. Let the equations rest. The universe will still be there in the morning, vast and patient and full of wonders, and you will wake up in it, refreshed, and maybe just a little bit more amazed than you were before. Good night. Sleep well. The stars will keep burning while you rest.